Today is going to be about these blast retrospective. Specifically, I'm going to focus on what is effectively an informational finding that simply because of a lack of a vulnerability. But I'm going to show you the steps that I took in order to demonstrate how Blast basically solved rounding errors and they solved loss of shares by using what they call the remainders and the shares logic. So our story will end here with the report that I wrote, and it actually starts with with my own notes. So I had to trim them down a bit just to not leak other stuff. As soon as the blast report is out, you guys can see what else was found. But this analysis will limit itself to kind of my logic more so than vulnerabilities. And so before we get started, we want to talk about what Blast does, which is different than how other system works. So our usual ER64626 vault looks a little something like this, where you basically have shares and you have, or rather you have assets and shares. And so given a certain amount of assets, you have to decide which direction to round in order to generate shares. And given a certain amount of shares, you have to decide which direction to round for assets. And that's not how Blast does it. What Blast decided to do, which I think is actually very elegant, is they decide that as soon as you deposit some assets, you are going to receive a certain amount of shares, which is going to be modulo a divisor. And so what that means is that given any deposit, there will always be a portion of shares, and there will always be a portion of remainder. So what this means is that in our hypothetical ER64626 attack, or in our good old donation attack, then as the assets increase, you effectively would have a loss of assets that is equal to a modulo shares of your deposit. That's simply because your remainder will be lost and your remainder will be socialized to the other shares because it effectively is a donation to them as you deposit. Whereas what Blast does is by dividing your assets into a share plus remainder, then what will be the remainder that is lost in the ER64626 donation attack actually ends up just being an idle remainder that you're still able to claim. It is still credit to you, but at the same time, it will not accrue value. So as I shift into my own repo, in this specific case, and I haven't run this repo for a few months, so it's gonna take me a moment, so bear with me. But the fundamental first thing that I did, as you can see that I'm in the Foundry Hack folder, which is my own scaffolding setup. The first thing I did is I basically ported over everything to my own repo. And I don't believe I cut out much. I simply made it so that the optimism repo or the Blast repo started at SRC instead of being a nested repo. That's just a convenience, and also because that way it works with Recon more conveniently. So that was the logic behind that. And when it comes to our scope, then we can start by looking at Weth Rebasing, which, if I'm not mistaken, is the contract that I attacked. You can see it here. And then I also have shares, which is basically just the underlying logic for handling how Weth works. And so, I mean, obviously I spent quite a lot of time on the contest, but fundamentally, when you look at what Weth is, this is just an adaptation of Weth that will use this withdraw and deposit function that come from the ERC20 rebasing contract, which, as I said, will use this idea of remainder and shares. So we can see here, the reason why I initially fuzzed the contract was really tied to some of these. Like, as you can see, setting a balance is not as simple as just storing a value in storage. Instead, based on different modes, you would have a different set of operations where, to make a long story short, we have the automatic, which, if I'm not mistaken, basically tracks your value for you. And you can see how the idea I mentioned about having a remainder and having shares ends up playing out. Then we would have two other modes. We would have the void mode, where a void mode basically assigns a fixed amount to you, and the fixed amount is basically stored as a remainder. So it basically doesn't accrue any yield. It actually is forfeiting its yield to the rest of the shares. And then lastly, we would have a claimable mode, which claimable mode will basically have the account. We will consider the account as shares plus remainder, but at the same time, it will force you to actually claim the yield from those shares instead of accrediting it to you, to your balance. And so that creates a scenario where the difference between an automatic and a claimable will effectively just be the ability of, or rather of claiming. So that was one of the first invariants I wrote, was my balance should match automatic after claiming. That's because if you think about it, a automatic balance is basically a claimable balance that is always claiming, with some nuance in the fact that if your balance is determined by a certain amount of shares and a certain amount of a remainder, then at least what I thought was that over time you would have to how do you say, you would have to account for the fact that somebody that continuously claim, they would actually increase their balance, when in reality, because of how remainders works, by definition, anything that is in a remainder will be left in the remainder, and anytime you have an amount that is greater than what will constitute the remainder, then it's going to get attributed to a share. And so there's actually a lot of elegance in this implementation that makes it so that the automatic accounts don't really have a loss, and we'll go into detail on that. But fundamentally, that was one of my ideas. The second idea was tied to the fact that just looking at the share value perhaps could have a certain amount of loss. And you can see how the logic here for each account basically multiplies the amount of shares that they have as well as their remainder. And we would also have this implicit property that a remainder would always be less than the value of a share by definition, because unless you're in the void mode, simply because in that case, then you will surpass. But that's also why the account uses this fixed storage variable, because the people that opt into the void mode, they actually have a separate storage slot, although the sum of their remaining shares is accrued here in this total void and remainders. So just the sheer complexity definitely led me to want to investigate this. And another aspect was the ability of changing configuration. I don't exactly remember where you would change the configuration. Change mode, maybe. Set mode. Set gas mode, but I'm pretty sure it was around here on the rebasing contract, where you would effectively be able to opt in and opt out. And once we go into the tester, you'll see that that was set up in order to test that behavior. And so that will be our ERC20 rebasing. And then we would have this shares base contract, which is basically in shares. And I thought the architecture here was interesting because, if I'm not mistaken, we actually have, in this contract, we actually have two declarations. We have this shares contract, which inherits from shares base. And then we have shares base, which is the contract that ERC20 uses. So first of all, we have a reporter, which means that only a specific address is able to make the yield change. But that also means that a yield report or a yield increase is actually a, how do you call it? It's a binary event, or it's a jump event, in the sense that once a reporter is ready to report, then we can expect in some way that our PPFS will go from a value to another value. And that's also something that I like to look into in code bases. It's just a great place to find bugs in general, is where the PPFS can jump. So that's something to keep in mind as well. Then we see this add value function, which is actually external, but internally it's instead is blocked by to make it so that only the reporter can do it, while this try distribute pending actually is basically meant to possibly fail, as you can see. And I think this assert false I added as a way to verify that we will always meet this condition. But fundamentally, looking at distribute pending and seeing how it could potentially fail also led me to believe that we could perhaps increase our shares, then cause the redistribution to happen, and in that way we could socialize some yield, or basically steal some yield, because we got the button to cause a redistribution. So having had those two kind of intuitions, that's where I started to dig deeper. And the way I did it, as I said, was by moving everything into my own Foundry test. No changes to the code, fundamentally. All of the code is the same. And then I used our good old recon setup, which at the time was very nascent, was fairly early time for us. So we can look at the setup where what I'm doing is I'm setting up the Weth contract, and then I'm setting up the shares contract. I then set an initial price, and I believe I added this function so that it would basically set it up as 1E9. I think because I removed this initialization, because I didn't want to deploy all of these meta contracts, just to keep everything simpler. And so we know that our initial price is 1E9. So what does this mean to us? This means that anytime we do a deposit, if we do a deposit that is below 1E9, or there's a remainder that is below 1E9, that's gonna be in our remainders. Whereas everything that is a multiple of 1E9, that's gonna be in the shares. So that's why it's such an important thing to keep in mind. And then we have the Weth rebasing, which fundamentally we simply set up and we look at that. And so you can see how add value could only be called by the reporter. So there is this almost stopgap aspect to the Weth, but then at the same time, you can see that the pending value is equal to the balance of Weth minus the yield bearing if minus the void and the remainders. So this is the sum of the fixed balances plus the remainders from accounts. This is basically the amount of if from the shares times price, because we have the underlying assumptions that each share, or rather each deposit of a certain amount of if, which is equal to the price per share, will yield a share plus a remainder that is always less than the value of a share. And so for that reason, our balance, anything that remains, is basically above that amount. And then you can see how the interesting aspect that I've always so clever in a way is that we will still have a remainder in this division, or at least we could have a remainder, which is basically the balance divided by the amount of shares. And so that remainder is cleverly kept in the pending for the next call. So that's how this contract ends up behaving. It ends up having a scenario where if it makes a share, it will make a share. If you donate to it, you're going to increase the pending. So that's how the pending get increased. And then if the division of pending over shares, which means that we cannot distribute this fairly, is left, then that's going to be depending of the next call. And so you could argue, interestingly enough, that the value of your deposit will be equal to the value of your shares plus the remainder plus the fractional pending, which is basically a value that is below one is below 1 unit, but it's basically that remainder of a unit that you would be credited if that unit were to round up, which in this case it's not, and so it's stuck until it will. And so with armed with this knowledge, then what can we think about? We can think about setting the price, and just to be fair to our setup, I think they will grab the initial price from shares. And so just to be fair, I didn't set the initial price to a massive amount. I set it to the shares price so that all of the setup was fair. It was not starting from a imbalanced setup. I then do an initial deposit just to give myself some tokens. And then like we can go to the target functions. And so the interesting aspect is, how do you donate in a permissioned environment? This is how you do it. You have the self-destructor contract. You basically create a contract that, given a recipient, will take whatever value it receives, self-destruct to the target, and effectively it will manipulate this address this.balance. And the reason why I did this was that it was clearly as part of the Optimism spec that they support self-destruct. And as far as I know, even now, technical mainnet, you can still self-destruct within the same block. So this use case is still valid. But as far as I know, on the OP stack, you can actually self-destruct even on a multi-block. Maybe this has changed, but I'm not aware of that, or at least I wasn't aware when I was doing the contest. I knew that this opcode was supported, meaning that the donation was valid. After that, we had the add value operation, which is basically effectively the one that will redistribute the price. Then we add a distribute pending, meaning that all of the pending value could be distributed. So let me see the definition for this one. It will basically call try distribute pending, which effectively calls it effectively increases the value of the shares that are the underlying contract of the Weth. And then the rest of the operations are about altering my balances and about altering my mode. So I had a transfer to self, where I basically transferred a token to myself just to see what would happen. I'm pretty sure I also have a way to transfer to somebody else. I then had a check to change my mode and trying to see if I could generate a additional balance there, just to see what would happen. I then had a claim to self. Basically, you will check for the claimable amount. That's obviously dependent on your mode, but going back to what claimable is the amount of rewards you can get when you have the claimable mode. So anytime you're in automatic or in void mode, you would have 0 claimable, but anytime you don't, then that's what you would do. You will check for that claimable, and the goal here was to ensure that you could always claim, provided that you claim a reasonable amount, and then also verifying that the sum of your balance would actually match the intended amount. And then we have a way to claim to self, which is basically, as far as I can tell, this is the same thing with the exception that we are checking an amount. So basically we're just passing a random amount and verifying whether that was above the maximum or not. And so fundamentally, by mixing these combinations, and if I'm not mistaken, I'm not sure where the other tester is, but I also went and I created another tester where I would have an actor that would always be in claimable mode and an actor that would always be in automatic mode, and I will verify that the actor that is in claimable mode would always match the actor that was in automatic mode, provided that they claim. And so by having all of these combinations, we're basically trying, by pure brute force, we're brute forcing the possibility of trying to go back from claimable to automatic, trying to go from automatic to void, etc. And so the only aspect in which you would have a fair loss would be when you are stuck in void mode because you basically forgave your own yield, and then another account is receiving the yield that you're generating. So those are the only scenarios that will cause a noticeable difference. But provided that you would always toggle from the active modes, which will be claimable or automatic, back to the void mode, and then you will immediately move the mode back, then what would happen every time is that you would have this dynamic where effectively you're basically converting your shares to the remainder, you're converting your remainder back to the share plus remainder. And so I was unable to create an arbitrage. I was unable to create a loss of yield. And the only thing that I was able to do was effectively demonstrate that there is a stepwise function in the yield. There could be a way to, move around that stepwise function, perhaps by contributing to a lower amount of yield, by trying to effectively, deposit here and then leave, simply because there is no vesting to this yield. It's always immediately deposited. But at the same time, in going through this exercise, I effectively demonstrated that this logic was actually really solid. So let's see what the Medusa coverage report looks like. Maybe, because as I said, I think I ran a bunch of these. So target functions. So let's see, we fundamentally, this is actually another report, so it's not the report that we would expect because it's from another run. So that was kind of the interesting research that I did. And I guess what I concluded, which is a pointer to a more interesting bug that, if I'm not mistaken, was awarded, but all I was able to assert is that, and as far as I know, what I'm about to say has no danger, there's no risk involved with it, but fundamentally, once you realize that this math is safe, then the only additional risk that you can imagine is trying to make it so that nobody can get any shares. And so what the interesting aspect of doing all of this was that in demonstrating how the math was sound, then the only solution as a hacker is to find an alternative path, simply because you're not going to escape this very simple, very safe logic of, if you are in the remainder, you're in the remainder. If you have a price, that's what you get. And so instead, what you could look to do would be to try and inflate the shares to such a point that you fundamentally are the only one owning shares, and making it so that everybody else gets nothing. So I guess, if you can only go left or right, the answer is to go up. And hopefully this shows you the type of thoroughness that you can go in order to make sure that no stone was unturned. So this is the report that I wrote. As part of the security review, I ran this test. I ran for 40 million runs, probably 4 hours, to be honest, because this was a fairly small scope. And fundamentally, we had the configuration transition, configuration reset, donation, increase of yield, transfer to self, and transfer to others. And in performing this test, we basically brute forced all of our checks to verify that fundamentally there is no way for people to lose money with this math. And so in conclusion, Blast, instead of trying to solve this balance game, Blast was able to solve the yield, the vault math or the shares math, by effectively asserting that given a certain share value, you will always be credited your share value and a remainder. So the remainder is almost, the remainder is stuck, the remainder is contributing to the yield but is gaining none of it. But by doing this, you make it so that in a more important fashion, as the yield is accrued, the share value grows, and the remainder, which could grow because of the modulo aspect of it, but fundamentally it makes it so that no single unit of asset is ever lost, because anytime a unit will be lost, it contributes to the remainder, and by the own property of the pending, it makes it so that if it was in the remainder, anytime it becomes divisible by the share value, it then is recirculated back and shared back to everybody else. So hopefully this gives you an insight into the work I did. I'm not sure who won the QA reports on Blast. Honestly, I have no idea. I don't have access to that information. But hopefully this gives you some insight into things you can test whenever you're dealing with yield, you're dealing with remainders, you're dealing with configurations, and you can work through that. So do you guys have any quick question for me? How do you reuse a corpus? Okay, so I'm gonna show you how to reuse a corpus with Recon and with your own work. So by default, let me see if I have anything. I guess we'll stick here. But by default, what happens when you run Echidna Medusa is that they create these folders with test results. Basically, they're just they're fundamentally just the data to reproduce calls. And then they have the call sequence, which is literally the list of calls that they're doing. So this is the corpus, and the corpus is automatically reused anytime you run Medusa again. So the way you reuse corpus is by doing nothing and just leaving that folder be, and it will reuse it automatically. That said, if you're working with Recon or you're working with other people, an example was the Curvens repo. The Curvens repo will take you 40 days to reach coverage. So in those cases, you need to reuse corpus. So I'm gonna show you how we reuse corpus on Recon. Basically, you run the job, and once the job is run, you just download the corpus, which basically means that you're downloading the entire folder, which contains the coverage report as well as the sequences, and you just replace the Medusa folder with it. So that's how you reuse a corpus that you got from the internet. The same thing will be if they hosted it on AWS or on GitHub or something like that. And then the way you can reuse corpus with Recon Pro is you basically grab the ID of a job and you go in the jobs page and you just paste it here. And by virtue of pasting it here, since you're using it on a job that is compatible, then the runner will clone the previous corpus and it will reuse it for the next run, which is how I've done. Eventually, I'll talk about all of the runs that I did for Euler, but that's also how I was able to redo multi-days runs in a few hours simply by reusing the corpus. So hopefully that helps you. But fundamentally, you are already reusing the corpus if you're not deleting your Medusa files. And as far as I know, with the new feature from Medusa with the corpus health check, it means that as long as the there's no bug, then Medusa will automatically triage the corpus you can use, and it will automatically scrap the corpus that it cannot use. Awesome. So thank you for joining me on this Thursday. I look forward to sharing more reports and more retrospectives with you. Maybe in a couple of weeks we'll do the Curvens one. But with that said, you guys have an amazing weekend, and I'll see you next Thursday. Have a good one. So this is a bonus just for the YouTube video. So as I mentioned before in the office hours, I also had a second tester where I compared the different users to see if I was able to generate a loss. You can see here I'm going to have a user contract with claimable and automatic, and you can see the modes are the respective modes. And the contract basically receives a reference to the token, which is set in the constructor, and obviously we set the mode as well. Then we have a way to reconfigure the mode, deposit, withdraw, and claim, and as well as transfer tokens to a random address. And obviously we needed the receive to be able to withdraw the Weth back. You can see that I then fundamentally just set stuff up, and then in my target functions I have my self-destructor for donations. I check my previous balance and the previous price. I verify, I basically grab the token balance of this contract and the token price, and I verify that I never lose tokens. That's because, you know, I should never, the balance should be 0, so I should never, that should never change. And then the token price, you can see that I verify that it never decreases, and it always goes above my starting price that I set, so that I could perhaps find a way to have that cause issues. And the main interesting aspect is, you can see here, we have a way to basically compare that the, obviously if we're in mode, if the token is in void mode, then we skip it. But basically we verify that shares plus value plus remainders is greater than or equal to fixed, which means that all of the tokens are correctly accounted. And then I guess we have a, you know, maybe this property is actually incorrect. Then I have a few operations here: donate, add value, distribute, etc. So fundamentally I just have the test for the previous stuff. And then the interesting thing that I have is way below here. It's actually here where I have my differential fuzzing, where basically I have a deposit for both accounts, withdraw for both accounts, claim for both accounts, and then I verify the balances here. Let's see. I basically check that I don't receive extra token, and then you can see that I basically have a stateful test where I basically verify that given that one account claims, then the other account always matches it. And then I have a way to reconfigure, and you can see that I basically have a way to swap all of this stuff. And so obviously, if you push it too far with some reconfiguration, you should be able to create an inconsistent state. But as long as you alter back from the void mode, or rather from the automatic mode to the claimable mode, then you'll see that the balance is always matched and it fundamentally is safe. But that's another example of what you can do, which is what inspired some of my later work on differential fuzzing, just to be able to verify that it actually works as intended. So hopefully that was interesting for you. Have an amazing rest of your day.